your first or maybe second, or let's say even third time with this club at a meeting. So if you're one of those three categories, tonight's your first, or your second, or your third, raise your hand. So we have a lot of new folks, or relatively new folks. So want to once again welcome you all here. And some of you have heard me say this before, but I'm going to repeat. It's always worth repeating, especially when we have new people joining us. What is this club all about? What do we do in the San Francisco Amateur Astronomers? Well, obviously, you're at one of our reliable, repeatable monthly functions every third Tuesday of the month. We meet here, with the exception of January, and we have a fantastic lecture brought to you by a member of the scientific community from the Bay Area over topics of very, very deep intrigue for someone like me, or all of you, we assume, who like science and who like astronomy. And we love this part of our monthly gathering where we get to learn something very, very exciting and very new. Usually it's very current, coming out of current research, and so we're very informed amateur astronomers that way. It's a lot of fun. Another thing we like to do as a club is we go out and go stargazing. And we do that as often as we can, and even when it's cold and wintry, you bundle up and you put on your warmest clothes, and we go out and we do star parties. So typically we'll have 2 per month, and most of you got a little slip of paper from me when you walked in the door, and we have a calendar, and it's pretty reliable. We are driven by the lunar phases, typically. So for example, when there's very little moon, we like to get together up on Mount Tam and have what we call the club members only night on Mount Tam. And that's one of the few things that you must join this club if you want to go do it. But if you haven't been up there, it's great, and if you have, you just know how good it is. When we're up on Mount Tam on a good dark night when there's very little or no moon, and the skies are reasonably cooperative, you can see the Milky Way, you can see many deep space objects. You have a bunch of us folks out there with our cool telescopes, and we have a great time up there. It's a very, very nice way to learn about the sky if you're new to it, and if you're an old hat at this, you share. And that's one of the benefits of being in this club, is our members only star party, which of course just happened, or would have happened last weekend except for the weather. The next one that's scheduled is going to be on, where is it here, December 12th, a Mount Tam Members Night. So these are on Saturdays. And again, that's a few weeks from now, a few phases through the lunar cycle, so that we don't have much moon. We also then intersperse with that city star parties. And the city star parties take place sometimes just over here at the parade grounds, sometimes out at Land's End at what's called Point Lobos, which is right near the Land's End parking area. And sometimes we'll do them right in front of the Exploratorium over at Pier 17. And we vary that from month to month, and it's on the schedule as well. And the next one of those coming up is this Saturday out at Land's End. So we'll be out there gathering pretty much at darkness, which is nowadays, what, about 5:30, 6 o'clock if you want to set up your scope. We enjoy the evening out there. There's always lots of passersby that jump in and join us as well. But that's a great chance, once again, without having to leave the city, to get out and enjoy the night sky. So I encourage everyone to consider that. 4 weeks after the one that's this Saturday will be December 19th, and we'll be back here at the Presidio Parade Ground. And what's fun about the Presidio is they put on a lot of other events here as well, and we've been out here at nights when all the food trucks are here and the fires are going, and it's really very, very lovely. So it's a pleasant place to spend time, and we enjoy doing that here in the city. Even though the seeing is not nearly as good as it up on Mount Tam, we still like to get out from time to time, and particularly in these public spaces where we get to meet and greet lots of people that are just stopping by by accident, if you will. But that's what we do. And then, as I mentioned, we don't have a club meeting in January. Why is that? Because we're going to put on our annual social event, and I want to encourage everyone in this room, whether you're a member or not, consider that. One of the things we enjoy doing also is not necessarily being out under the stars or being out at a meeting like this, but just having a good time together, to get to know each other, to make some new friends, to have some pleasant time together, having some drinks and some food. So we'll be doing that. It's on your calendar right here. It's on January 23rd. It's on a Saturday. And again, for many of you, if you're thinking, well, I don't know about these people, they're kind of weird and they're all into astronomy and they're kind of geeky, it's okay. Like, we're super nice, okay? And we're social too. And we get out of our telescopes and our cold nights sometimes and go indoors and socialize. So I want to encourage everyone to show up for January 23rd. Now, I'm going to do a little bit of survey right now. So we're not yet settled. We were just debating this an hour and a half ago in our board meeting, where we should do this precisely. And we have a couple different options in place. You know, if you're going to go out to our awards and social night, you know, there's more relaxed and informal, and there's a little bit more swanky and formal. So I'm going to ask everyone in the room, even if you're not going to go, to express an opinion, okay? And you have one of two choices. I just said them. So raise your hand if you would like the less formal, more relaxed setting. Hands, looking around. Board members taking note. And now let's put those hands down. And now the ones that prefer the more swanky, a little more upscale. Oh, ooh, wow, ooh. I think the audience has voted on that one, haven't they? Well, that was going to go with the second question. You know, we have to charge a fee for this. We can't give away dinner for 50 or 100 for free, so we have to charge a fee. So we want to keep it low. So I think what you're all telling us is if we charge a moderately low fee and make it comfortable and casual, I think a lot of you are coming, right? Is that what you just said? I think that's what I just saw. And we should. You should get together with us. Like I said, we don't have a club meeting explicitly for that reason, because we want you to come out to our social event and be social. So that's what's happening in January 23rd. Mark your calendar. Okay, one more thing before I stop, and that is that we are in a little bit of a season where you can see meteors. So tonight, right now, today, November 17th, on my birthday every year, we have an annual meteor shower. Tonight's meteor shower is called the Leonids. And what happens when the Leonids come in? Well, actually, we've had the Taurids, haven't we? We've had fireballs. I've seen people reporting that on the Facebook page. So what are meteors, right? Let's do a little mini lecture from Paul. And the mini lecture is as follows. You know, we're here on Earth. We're flying around the sun every year. We go through debris streams, right? So there are comets that go around the sun. There are asteroids that go around. There are just space junk. And sometimes it's in a reliable spot where every year on November 17th, for example, we go through a bunch of debris, and that's happening as we sit here right now tonight. But also, what's kind of cool about meteor showers is that there are meteors you run into if you're on the Earth. Here's the Earth, and we're moving around the sun like this, and we're rotating around every 24 hours, right? So it's evening, we're over here. By morning, we're going to rotate around, and we hit more meteors. You all follow that concept? We're on the front face of the Earth. So typically, meteor showers get really quite good the later you can stay up. And in fact, now that it stays dark so early in the morning, if you're a morning riser and you're up at 5 a.m., look outside and I'll bet you'd spot a few meteors then as well. Because that's the best time to see meteors, is actually after midnight and through the wee hours of the morning. And the best meteor, one of the best meteor showers of the year happens in the summer. It's called the Perseids. But the problem with the Perseids is that it starts getting bright again at about 4 or 5 in the morning because it's summer. So here in the winter or fall, you have a better shot at seeing those early morning meteors if you want to see some tomorrow morning or even late tonight. But the best way to see a meteor shower is just to look up, to be in a relatively dark spot. Even if you're here in the city, it's a beautiful clear night tonight. I bet you'll see some. And in addition, we have this thing called the Taurids, which are happening right now, and those are been many slow, large, bright fireballs. And so if you look at our Facebook page, you'll see a couple of our members have reported seeing some of the recent Taurids. The Taurids don't happen in one night. They happen over a period of several weeks. And the last one I'll talk about is the Geminids. The Geminids happen next month. December 11th and 12th and 13th is the annual Geminid meteor shower. And for what it's worth, that is actually one of the best ones of the year. It definitely rivals the Perseids during the summer. But it's awfully darn cold outside, so fewer people take the time to go see them. But if you can stand bundling up and getting in your best sleeping bag and warm gear and popping out in your backyard if we have clear nights around that time, I love the Geminids. The Geminids are a great meteor shower. So I would just want to encourage that you don't just look at the astronomy and enjoy it for the telescopes. That's part of the journey. Part of it's through binoculars, part of it's naked eye, and part of it is just being patient and relaxed and enjoying things like meteor showers as you can do tonight. So there you go. Those some meteor showers to think about tonight, the Leonids, and in December timeframe, 11th, 12th, 13th-ish, the Geminids. And with that, any other announcements? Anyone in the club have anything else we have to announce right now? Left anything off? Linda. So we're going to introduce Linda Mahand. She's the coordinator of our monthly lectures and an extraordinary member of this club who's been dedicated to bringing in some of the best talent for years and years. So Linda, thanks.
The job is so easy in the Bay Area with the wonderful institutions that we have. Oh, I need to bring it down to here. Is that good? Can you hear me? This is a wonderful area to find excellent speakers, and I'm so glad you're all here. I just wanted to mention on December 15th, Greg Delory from UC Berkeley Space Sciences Laboratory is going to give a talk called Water, Water Everywhere, and I bet it'll be raining that night. From Earth, the Moon, Mars, and beyond. So water, essential for life as we know it, is an important indicator of conditions on other planets and moons, and he'll discuss results from recent space missions on the topic of water. As we know, no January meeting on February 16th, Brian Day from NASA's Solar System Exploration Research Group is going to give a talk called A Hard Rains Are Gonna Fall. And this is about rocks from space. He's going to talk about Chelyabinsk and other near-Earth objects, and even comment about how amateurs are helping in the finding of these objects. March, Amy Furness is going to talk about the violent universe observed with the Fermi Gamma Ray Space Telescope. I'm awaiting April's confirmation, but in May we're going to have a talk I'm extremely interested in hearing, and Mark Showalter is going to talk about news from the recent close encounter with Pluto. By then there'll be more and more interesting information that he'll share and images with Pluto. Tonight I'm very pleased to have Aaron Lee give a talk to us. He's a graduate student astronomer and dissertation fellow at the University of California, Berkeley. He received undergraduate degrees from Northwestern and Cambridge University. His research focuses on the formation and evolution of both stars and planets across all cosmic time. Currently, he is researching the formation of the first stars ever to form in our universe using some of the most powerful supercomputers in the world. He sifts through hundreds of terabytes of data in order to complete his research, which has been published in leading astronomical journals. And he's also a passionate public advocate for astronomy and science communication and education. He often works closely with Alex Filippenko, who many here have heard speak and see him on television from time to time. He's running Alex's immensely popular introductory astronomy undergraduate classes. His dedication to teaching has been acknowledged by his students and the university, having received teaching awards from UC Berkeley and numerous accolades from his fortunate students. Tonight's talk, Ending the Dark Ages, the Universe's First Stars. Our 14-billion-year-old universe has generally been filled with stars and starlights, but here on Earth we orbit one such star, and it's been shining brightly for about 5 billion years. But what about the first star? How did it form? What did it look like? What was the universe like when this first star started bringing the universe from a place of darkness to a place of light? He will discuss how stars form and evolve and how their environments play a significant role in their development. And we'll look especially at the universe 500 million years after the Big Bang, when these very first stars began to form. We believe that these stars played a significant role in the development and evolution of the universe, as well as the eventual development of intelligent life. Join me in welcoming Aaron Lee.
All right, before we start, I think I'm supposed to press record, and hopefully something will happen. Did I write that abstract? That was really good. Thank you so much for having me here at the San Francisco Amateur Astronomy Society. It's a pleasure to be here, and I will understand completely if your attention wavers, because this view cannot be beat. So this is a great venue, and I'm happy to be here. So we are going to talk very generally today about star formation in our universe. And while my research focuses right now on the formation of the universe's first stars, this will be a general talk on star formation in general. I like to focus on big pictures. You can, of course, ask me about the details afterwards. I'm happy to stay and answer any sorts of questions. But I'll try to stick bigger picture and overarching story. And so some of the things you hear today you might have actually heard before in other contexts. But I find them so fundamental, and sometimes it's hard when you hear bits and pieces on programs and news and articles to get a sense of what the bigger picture is and how all of these things tie together. So yes, we live in a universe filled with stars. Particularly, we orbit the sun. And sometimes we take the sun for granted. Where did the sun come from? How did it get here? We know how the sun will continue to shine as it fuses hydrogen into helium in its core, a core of 15 million degrees. We know that it will live for about another 5 billion years or so, and then will proceed to a red giant and eventually ending as a white dwarf. And we are starting to piece together a picture of how stars like the sun may have formed in the first place. And so this talk will investigate the formation of objects like the sun and stars that formed earlier in the universe. We now know over 400 billion stars just in the Milky Way galaxy. Aristotle thought that the heavens were immutable. When he looked up into the sky, it appeared to be never changing. There were the occasional few wandering bright objects in the sky that we eventually came to know as the planets. But other than that, all the objects that we saw in the sky were always in the same place, night after night. He thought the sky never changed. The stars were always there and always will be there. But it wasn't until 1572 when Tycho Brahe noticed a nova stella near the constellation Cassiopeia, a bright star that appeared out of nowhere and gradually faded over a couple of months. So the heavens changed. There was something that happened that caused the heavens, the sky that seemed to be the same night after night, to change and evolve and become something different. So he called this a nova stella, a new star. We now know that it actually wasn't a new star, but it was a dying star. This was a supernova explosion that we've been able to look at in more impressive detail using modern telescopes. But it shows that stars do not last forever. We also can look at other regions of the sky, like the Orion constellation, one of my favorite constellations, mainly because it's one of the few constellations I know. If you ever want to feel impressive, ask a theoretical astrophysicist like myself to do a competition to identify stars in the sky. You'll be baffled at how few of us actually know any of the constellations. But I do know Orion, because Orion is one of my favorite. You get all sorts of stars. Particularly, you get the Orion Nebula, the region in Orion that you might imagine where his sword would be. It's not an individual star, but it's actually a cloud of gas that has thousands of times the mass of our sun in gas and dust floating around. And some of that gas and dust is collecting and forming new stars as we speak. So stars can form. We can look at these stars and using analytical models tell that these stars have recently come into existence. Recently meaning in the last million years or so, which is nothing when you think about astronomical situations. So stars form, stars evolve, and stars die. So that suggests that there was perhaps in a universe that we now know to only be about 14 billion years in age, there must have been a first star. There must have been a moment when the universe went from a place of darkness to a place of light. When something happened that caused the first star to turn on. And I really think that this is the moment when the universe really starts to live. Because before the first stars formed, we'll see that everything was more or less very uniform and very dark and just kind of hanging out. Gravity, with only gravity doing its thing. But then when the stars turned on, that is when really the universe started to know itself. And these stars have played a significant role in the evolution of the universe and in the evolution of intelligent life here on Earth and perhaps elsewhere. We now know that the iron in our blood and the calcium in our bones originated in stars. Carl Sagan's famous quote, "We are made of star stuff," is very true, and that the calcium in our bones and the iron in our blood was once formed in a star and then ejected into outer space either through a supernova explosion or through something like a planetary nebula. That material was recycled and eventually formed the Earth and formed us. But that process had to get started at some point, and we owe so much to the stars. So this talk is about those stars and their story. So to begin, I want to talk a little bit about how astronomy is possible and how we as astronomers know what we know. The short answer, of course, is telescopes. We know what we know by collecting light from a variety of different objects, using different telescopes for different techniques. Sometimes telescopes don't quite look how you might expect them to look, like the Very Large Array here. Where these, it's a radio telescope, so it looks at radio wavelengths, where by having a bunch of these telescopes that are each only about 25 meters in diameter, but they're spaced in this interesting configuration that's 25 or 22 miles across. They all can work together and operate as if they were a single telescope 22 miles in diameter. So we can get ridiculous, unprecedented resolution just by having all these telescopes kind of syncing up and working together. So we collect that light, or we collect this radiation, with a soup son of analysis. We can make some of the startling conclusions that we make. Now, I feel that this is often how it's stated that astronomy proceeds, and if I left it there, I feel that would be really unfortunate, because it doesn't really get at the heart of one of the most simple yet absolutely profound implications of light that allows astronomy to do and operate as it does. And that is that the fact that light travels at a finite speed. And that allows us, since light travels at a finite speed, it allows us to observe the universe across its entire lifetime. Consider the apple. If I have an apple on a table and I want to see that the apple is there, light has to bounce off the apple and then travel over to my eye. Now, the speed of light is pretty fast, 1 foot per billionth of a second. So it appears instantaneous. There is no delay in when the apple appears on the table and when I see it. I cannot perceive that sort of delay. But nonetheless, there is a delay. It takes time for light from that apple to make it over to my eye. That takes time. So by the time that snapshot of the apple makes it to my eyeball, time has passed. So the apple has aged a little bit. You can think of light as a Polaroid snapshot. And that Polaroid snapshot is flying through space until it hits my eyeball. And then I see that exact Polaroid snapshot. But in the time it's taken for that Polaroid to get to my eye, the apple might have aged. And as time progresses, the apple, what I see reaching my eyeball, may not be necessarily representative of what the object looks like at this very second in time. Light takes time to travel. Now, the way I phrase it, this might seem discouraging and you might never eat apples again. You're always taking a risk when you bite into that apple because you're always seeing it ever so slightly in the past. Who knows what has happened in that time between picking up the apple and taking a bite. But we can flip it around. In that sense, light takes a finite time to travel. The snapshot that reaches my eye allows me to glimpse into the past. And that I can see how that apple appeared, in this case, a few billionths of a second ago. So our eyes can act as time machines, or telescopes, which will act as our eyes, can act as time machines. Collecting light from more distant objects allows us to look farther and farther into the past. I always bring up this fact when I talk with kids in elementary schools and junior high schools, and I phrase it as, is it possible to time travel? Is it possible to look back in time? What if I told you it's possible? And they all get really excited. And then when I give them the answer, they are so disappointed. But I think that shows, this very simple fact, they might not be quite old enough to appreciate this, but this is actually quite profound. Some of you at the end of September might have glimpsed at the lunar eclipse and saw the supermoon, the blood moon. But you aren't seeing the moon as it appeared 1.3 seconds ago. Because the light that bounced off the moon and heads eventually ending its journey at your eye had to travel 250,000 miles through space to get to your eye. These stunning, stunning images of Pluto that were taken by NASA had to travel through space for 7 hours after the photo was taken before it could actually make it to NASA back here on Earth. I cannot imagine working at NASA knowing that New Horizons had taken the photograph and then just having to wait 7 hours as that photo was flying through space, hoping that when it finally made it to Earth, it would look something like this. So in the solar system, maybe this finite speed of light thing is more of a nuisance. It's kind of annoying. But if we go further out, it starts to become more and more important. The Andromeda Galaxy. We are seeing the Andromeda Galaxy as it appears 2.5 million years ago. Early hominids were starting to walk across the Earth. When the light that we are seeing, when you look through a telescope during one of your observing parties, that light started its journey when early hominids on the Earth were starting to walk around. A more local example, the Orion Nebula, is 1,000 light years away, which means we are seeing the Orion Nebula as it looks 1,000 years in the past. And we can go even more extreme. In this box, we can zoom in, and in this box, we can zoom in, and we get this smudge of light, which we now know that light from that red smudge has been traveling for 13.2 billion years. So, using the fact that light travels at a finite speed, that means that light was emitted when the universe was its current age minus 13.2 billion years old. Or that light, this light we are seeing here, was emitted when the universe was only about 600 million years old. And it's 14 billion years old now. So the light that we see here gives us a glimpse of what the early universe was like. You might say, what the heck are we learning from this? Give me some time. The takeaway is that by looking at objects at varying distances, we can get a sense of how the universe looked at different points in time. By looking farther and farther away, we are also looking farther and farther back in time. So to find things like the first galaxies and the first stars, we have to look even farther away, which is very difficult. But if we can do that, we can piece together a scrapbook of our universe and the objects in it and how they evolve and change. Another thing about light that's worth mentioning is that we astronomers historically only used colors of the rainbow. They only used the light that we can see with our eyes to study the night sky. But astronomers now can use all different sorts of light. So light, like you're familiar with, is one form of what's called electromagnetic radiation. It is a wave phenomenon. You can understand it as a wave, where if I define a wavelength, which is just the distance between a trough and a trough, or the distance between a peak and a peak, tell me only the wavelength, and I can tell you how that light is going to behave with matter. If it's a certain wavelength, it might appear as red. If it's a slightly smaller wavelength, it might appear as blue. If it's even smaller, it becomes ultraviolet light, or what gives you a sunburn. If it becomes even smaller, if I squish this wave together, it turns into something like an X-ray. Alternatively, if I stretch this light beam out farther and farther and farther, so it has a very long wavelength, it starts behaving not like red or blue light, but like a radio wave. Things like radio, X-rays, visible light are all examples of one certain type of phenomenon called electromagnetic radiation. So whenever I say or mention the word light in the rest of this talk, I'm not just talking about colors of the rainbow. I'm talking about all different sorts of electromagnetic radiation. And different types of radiation are emitted by different sorts of processes. So by looking at the entire spectrum of the electromagnetic radiation, all the way from radio waves, where the distance between trough and trough might be the size of a house, to visible light, where it's something like 1/10 of a micrometer or hundreds of nanometers, all the way down to X-rays, which can be near tens of a billionth of a meter. These different kinds of light are emitted by different processes. We're familiar with a few of these. Visible light like the sun, a type of light that's called infrared radiation. Typically it's associated with heat because it's the type of radiation you give off. We are all glowing right now. We cannot see that we are glowing because our eyes have evolved to look at visible light, which we are not giving off. We are emitting infrared radiation instead. Yeah, the thing that always tricks introductory astronomy students up is when I show them an orange basketball and ask, is the basketball emitting orange light or is it reflecting orange light? It throws them off a little bit. This shirt looks black and white, or these pants look blue, not because they're emitting blue light, but because they reflect blue light. But if I looked at my body using an infrared camera, or if my eyes had evolved to process infrared light instead of the colors of the rainbow, my face would glow very brightly because my face is giving off a lot of heat, where my shirt and my pants might not be giving off as much heat as my body. And then X-ray and radio are some of the familiar examples we have on Earth. But this type of radiation is also emitted by objects in the universe. So the Keck telescopes, the telescopes on Hawaii, are built primarily to look at things like visible light and a little bit of infrared. The Very Large Array is built primarily to look at radio wavelengths. So you would not use one of these telescopes to look at something like the colors of the rainbow. But you can use one of these telescopes really well to look at something like radio waves. And then we also have the telescopes in space, like the James Webb Space Telescope. God willing, it flies in a few years, it is built and will look primarily at infrared radiation. And then there are other space telescopes like Spitzer or Swift, which look at things like X-ray and gamma ray, which make more sense to look at from space because luckily our atmosphere blocks out that type of radiation really well. Good for us, bad for astronomy research, because that means we have to go out into space, which is much more expensive. So we use all different kinds of radiation. So that's what I mean by light. All the different types of radiation, from radio to including the colors of the rainbow, up to things like X-ray and ultraviolet. Now we can use this light in two different ways. One way of doing it is a direct image. Get an actual image of the object. The selfie is an example of a direct image, where you take a picture and you can assess the actual structure of the object because you can see where the light is coming from. This appears bright because there is more light coming from this part than this part, so it allows me to discern that there are shadows and there is structure on the surface of the moon. Another example, if I look at a galaxy in visible light, I can see that there's a shape that looks like a galaxy. It appears brighter in the center, which might suggest something. But I can also look at it in the infrared wavelengths and see different aspects of the galaxy. Particularly, you notice that where it's dark in the visible picture, so there's not a lot of visible light, not a lot of colors of the rainbow being emitted at these dark spots. There's actually a lot of infrared radiation being emitted at those dark spots. So these regions aren't dark because they're empty. They're actually dark because there's so much stuff there that it's opaque to regular light. But that stuff is actually glowing at different wavelengths, in this case at the infrared. Another example, if you looked at this in visible wavelengths, it looks, I see some wispy filaments, kind of looks maybe like a cloud in space, I don't know. If I looked at it in infrared wavelengths, I see more or less the same thing. But if I look at it in X-ray, it looks like a giant bubble. So something that created this structure emitted a lot of X-ray radiation. It turns out X-ray radiation is much more powerful. It packs more of a punch than something like visible light, like red light, or something like radio waves. So we now know, by looking at this object, by taking a direct image of it at various wavelengths, we know that this is a supernova remnant. This was once a star that exploded as a supernova. And by looking at exactly how much light is being emitted from different parts, that gives us a sense of actually what went on during the supernova explosion. The fact that it's not a perfect ball suggests that the supernova was not a spherical explosion, but it was a little lopsided and messy. More was exploded out in this direction than, say, this direction. It is not. This is the Veal Nebula. 1987A is also a stunning picture, one worth Googling. But that's also an example of a supernova remnant, right, which we can actually see, we can actually directly image. But direct imaging has its limits. Again, we go back to this guy. I am not seeing a lot of structure in this red blob. I claim it's a galaxy, but there's no reason based on this picture that you should believe me. That is actually a galaxy from the early universe. So direct imaging becomes hard when objects get very, very far away. And actually for something like a star, even though a star is very big by our standards, when you look at stars in the sky, they look like literal dots. When you look at a star in a telescope, that's not the sun, they are still literal dots. You know, it's very hard to actually image a star. There are, I think, only 1 or 2 stars that we actually can directly image besides the sun. And even then, it still more or less looks like a little fuzzy ball. We don't get a lot of detail because they're so far away and so small in size. Versus something like a galaxy, which are so huge that even though they're very far away, we can actually still make out some shape. But not to fear, there's another way we can use light. And that's through spectroscopy, where rather than measuring where the light is coming from on the object, we measure the relative amounts of light that's coming from the object. So we want to see how much red light is coming from this object versus how much X-ray is coming from this object versus how many radio waves are coming from this object. So this is called spectroscopy. It's more or less when you have a telescope and light comes into the telescope, you throw it through a super expensive prism, more or less. Then you break the light into its different components. So then you can break out and then count how much red light came in, how much blue light came in, how much green light came in. So the background image that you see is a spectroscopic image of the sun. So when we look at the sun, particularly at visible wavelengths, so colors of the rainbow, we see that it emits different amounts at different colors. For example, it's very, very bright in the yellow and the green, but when you get up here to the darker purples, it's much darker, and there's not a lot of purple there compared to yellow and green and some orangish red. Then also notice there are all these little dark spots, where at some particular colors, like that particular color of yellow and that particular color of green, there's a deficit of light. Light just happens to be missing. And that actually tells us a lot about the object. Because of these dark spots, we know exactly what the sun is made out of. Each of these dark spots is a fingerprint of different atoms that are in the sun. Because different objects and different processes emit different kinds of light. And so by looking at how much light from an object we are getting, we can assess what sorts of, and then through some modeling, we can assess what sorts of processes are occurring on the sun, as well as what sort of composition makes up the sun. Which is amazing, that we know it to very, very high precision, the composition of the sun, and we have never actually gone to the sun and directly measured its composition. To directly measure the composition would mean we travel to the sun, scoop up a bit, and look at it. But just by looking at the light it emits, we can tell not only what the sun is made of, but this actually also helps us, along with modeling, determine how old the sun is, how big the sun is, how long the sun will live, and that sort of thing. Beyond the sun, we can do this with other stars. Again, since we cannot make out the actual shape and structure of the star, because they just look like literal dots, we can do spectroscopy on them and look at the relative amounts of light that we see from these objects. So in this case, this is a small star, so a star that is smaller than the sun. I think it's like half the mass of the sun. This is an average star like the sun. The sun is an average star. If you randomly pick a star in the sky, it's more or less going to be similar to the sun. And then this star is a star that is brighter than the sun and bigger than the sun. It's a few times the size of the sun. And we can notice that they emit different amounts of light. The big star emits, you can see it's much brighter in the purple than this star, which appears very dim in the purple. And this particular star, you can see there are some dark lines in the yellow and the blue that don't appear as strongly or at all for these different types of stars. So these dark lines here actually allow us to pinpoint that there are molecules on this particular star. It's cold enough that things like molecular, I believe it's molecular nitrogen and other smaller molecules can actually exist on that star. It's not hot enough where those molecules will be broken apart. But in these guys, since we do not see the dark lines, that implies that this star is much hotter. And so that things like molecules cannot exist. It's much too hot for something to stay as a molecule. Those atoms would easily be broken apart and things would just roam around as atoms versus binding together. So this actually is key when we look at the very distant universe, because then we can see, by looking at the different amounts of light, we can get a sense of the different types of processes that are occurring in these objects. And then through some modeling, we actually can learn everything we need to know, even though we can't actually see the object directly, like we can see the moon or we can see our own sun. So with that, let's move on to star formation in today's universe. So if we want to talk about star formation at the very beginning of the universe's life, it helps to understand how we think stars form today, because that will inform our models of the early universe. So again, my favorite example is going back to the Orion Nebula. The fuzzy patch of light that you can see with your naked eye. And we can ask, if I want to form a star here, an object that is fusing hydrogen to helium, and I'm pretty convinced that stars are forming here. What is going on in this location that is allowing stars to form? First thing we can do, since we are not limited to only looking at the colors of the rainbow, is that we can look at the Orion Nebula using different kinds of light. So if we look at the Orion Nebula using infrared radiation, same exact part of the sky, you can see that these three stars are still those three stars right here. The Orion Nebula is actually part of a larger complex of gas and dust. It is part of a larger molecular cloud, we call it, a cloud of predominantly molecular hydrogen. And there's a lot of it. There are thousands of times the mass of the sun in gas flying around in this region. Plenty of gas to form something like the sun, which only weighs the mass of the sun, versus something that is thousands of times the mass of the sun. So here is a general kind of simple picture model of how we think stars form. You have this giant cloud of gas. And left on its own, gravity will pull things together. If you're ever at a party and someone asks how blank works in astronomy, where blank can be more or less anything, the answer is generally gravity. So stars form predominantly through gravity. I need to get gas in a small enough space so that if I cram enough gas in a small enough space, it will get hot enough that nuclear fusion can start. I need to get that core to 15 million degrees, which it's not going to do just kind of floating off in space. I have to compress it by many orders of magnitude. Gravity does that very well. Gravity does not discriminate. Anything that has mass, gravity will pull together. And so when you have a giant cloud like this one, gravity is always trying to pull all that gas into a smaller and smaller space. And so the idea is that if you have a large cloud of gas, gravity will start doing its thing. But unfortunately, gravity is not the only player in the game. If gravity were the only thing that was happening, we would get stars, easy peasy. But pressure fights back. And what do I mean by pressure? I mean thermal pressure. The same pressure we are feeling in this room with air pressure. On your skin, there are molecules that are flying around this room that are bombarding your skin. They exert a pressure on your skin. Same sort of thing, but now we're out in space. We have molecules of gas flying around in space. Occasionally they run into each other, and that impact packs a punch. So as gravity is trying to pull things in, pressure is starting to push things back out. Think of the balloon. When you blow up a balloon and are holding the nozzle closed rather than tying it shut, the surface tension of the balloon is trying to go back to its unblown state. But the pressure, the gas that's inside the balloon, is pushing back on the surface of the balloon, which keeps it filled in the shape of a balloon rather than just a deflated balloon, as long as you hold it closed. Once you open it, the gas escapes, and end of the story. But here, pressure is fighting back. So you need to get enough stuff so that gravity ultimately wins over pressure. If the pressure were to stop gravity in its tracks, you would never get to an object small and dense and hot enough to form a star. So one item in your recipe to form a star is just get a lot of gas. Get a lot of gas in a small space, because then gravity will be able to do its thing. And the more gas you have, the more gravity you have. What's also convenient is if the gas is cold. So the molecules in this room are bombarding my skin at a certain speed. If I were to heat up the gas in this room, All that means is that each individual molecule in this room is moving around faster. Temperature is just measuring how the average energy of a particle. So the higher the temperature, the faster the particles move around. And if a baseball runs into my face that you've thrown at me versus one you've kind of gently tossed towards me, the one that's thrown at my face is going to hurt a lot more. So higher temperatures means the particles are moving around faster, they pack more of a punch. So ideally, if we want pressure to fail and for gravity to win, we want a lot of gas, and we want that gas to be as cold as possible. When that happens, we think then gravity does its thing. The cloud gets smaller and smaller and smaller. It doesn't all necessarily go into the same spot. Sometimes it gets clumpy. We'll look at a simulation in a little bit. And sometimes it clumps up, and in each of these little clumps, as long as gravity remains strong enough, it can get small and dense enough to form an actual bona fide star. So when we look in the Milky Way, or when we look in today's universe, where might we think stars can easily form? Well, first step is you want to have a lot of gas. So where is there naturally a lot of gas? We look to the spiral arms of spiral galaxies. Notice in this simulation, as you see particles move around, you can think of each of these particles as a big blob of gas. Spiral arms, the best analogy we have for a spiral arm is a cosmic traffic jam, in which particles and stuff from space move into the spiral arms, kind of hang out for a while, and then if you watch closely, you'll notice those particles then eventually leave on the other side. Spiral arms are just giant cosmic traffic jams. So it makes sense that when we look at galaxies in our current universe and in the Milky Way, we see star formation occurring primarily in the spiral arms of spiral galaxies, not in between the spiral arms, and not in weirder galaxies like elliptical galaxies where you don't have spiral arms and everything is more or less just uniformly spread out. Look to the spiral arms where gas has naturally collected. Now we also need to make this gas, once it gets into the spiral arms, it'd be convenient if we could make the gas really cold. The way we do that is by dust. And when I say dust, I mean exactly what you're thinking. Very tenuous compositions of carbons and silicates, very similar to the dust that we deal with here on Earth. Turns out these sorts of structures are very good at absorbing radiation or absorbing heat and re-emitting it as radiation that escapes. In fact, this bright light you're seeing in the dark regions is the light coming from dust. So dust is very good at absorbing heat, so then the overall temperature goes down. But it has to get rid of that energy somehow, or else the dust would just get hot. So it's able to throw that energy away by emitting it as infrared radiation, which escapes out into space. With that, we can bring the temperatures of these regions down to something like 10 degrees above absolute zero. That's pretty cold. To give you a comparison, it's 300 degrees above absolute zero in this room. I'm thinking of the Kelvin scale. So it gets pretty cold, and you have a lot of gas that naturally builds up. So let's take a look at a simulation. Not of my own, but of a colleague over in England. So what he did here is he took a giant ball of gas, kind of stirred it up a little bit, so it's not completely uniform. He stirred it up a little bit. And then we're just going to let gravity go. We're going to let gravity turn on and see if it can beat out pressure. So try to look and see what things you notice. So first thing, gravity starts to really start clumping things together. You got a big clump here. That seems like a great place to look for where stars might form. Here we're adjusting the color bar so we can zoom in on this interesting region where you got a lot of gas in a small space. We'll eventually zoom in a little. You'll see some white dots flying around. Those dots are protostars, or little objects that will eventually become stars. So gravity has won in those little regions. They will become each individual stars. So as this happens, gravity is, when a star forms, gravity just doesn't turn off. Gravity keeps going. All the while, you have all this gas flying around. Look at this guy. What does that look like when you look around that star that's forming? Yeah, like kind of like a spiral galaxy or some sort of disky shape. So it's interesting because you're seeing more or less like a smaller version of a spiral galaxy, but now it's just one individual star with a lot of gas flying around in this disk. You see lots of stars forming. Some of them are thrown out. You got this one, looks like a little binary, where you notice there were two individual stars kind of orbiting around each other. So gravity succeeds in forming lots of stars just by letting gravity pull things together, as long as you can get enough gas and can get the gas cold enough. Give you a sense of scale, that ball was about a light year in diameter, and it formed, a few dozen stars.
Did it start without angular momentum?
So it started, so there was a little bit of angular momentum, very, very little. When you have things that are kind of randomly mixed together, you inevitably have a little bit of rotation. So when I say angular momentum, I mean slight rotation, which plays a role. Notice how we saw that disky structure form around one of those stars. That was a result of that slight rotation when things are very big, kind of being amplified as things get down to being very small. This is the same kind of process as when an ice skater spins when she holds her arms out versus when she pulls them in. She spins slower when her arms are out and then spins faster when she pulls her arms in. We saw that, for example, when we saw that disk around one of those stars. That slightly rotating gas got spun up into a disk as it got smaller and smaller.
The temperature was 10 to 10 Kelvin.
Around 10 Kelvin, yes. These star regions, dust is a very good thermometer. And as long as you have a little bit of dust, you can more or less stay at 10 K and nothing's going to happen. Except, for example, like around the star where you have starlight and stuff like that. Yeah, so it's kept very cold, so gravity can do its thing. But yeah, I pointed out one of those disky structures. And we have seen these disks. When we look in the Orion Nebula, we can see newborn stars and see these dark little regions that look like disks of gas around these newborn stars. And so this informs us of how we think stars form today and what a typical picture of star formation looks like. You first get gravitational collapse. As this happens, a disk typically forms. As you said, you have some angular momentum, or you have slight spin that gets spun up, and all this material kind of falls into a disk. That disk then starts to feed the inner star, so all the star continues to grow, but it's getting its material by the disk kind of dropping material into the center. And it turns out in that disk that we saw is actually where planets are forming. So when the solar system formed, the sun presumably formed by a process like this. There was very likely an accretion disk around the sun. In that disk is where the planets of the solar system, like the Earth and Jupiter and Saturn, formed. At the end of the day, the disk eventually runs out of material. There's a lot of material in these star-forming regions, but there's not an unlimited amount of material. So eventually that star gobbles up all its surrounding material, and this disk gets depleted, or it gets blown away. But once the star really officially turns on, all that starlight can blow away some of the remaining disk material, leaving behind a star, a bona fide new star. Gravity has won that game, with perhaps some planets that were made in this disk before it got blown away or eaten up. So planet and star formation are intimately tied together. And this is a general picture on how we think our own sun formed and how the planets of the solar system formed. It gets a little more complicated when you think about massive stars. So again, I said the sun was an average star. But we also know of stars that are like 30 to 40 times the mass of the sun. They likely formed in a very similar way, but they actually start harming themselves in a sense, and they make it harder for other stars to form in their vicinity. We've all likely seen the pillars of creation in the Eagle Nebula, where there are new stars forming in these dark regions right here at the tips. If we were to look at the same picture in infrared, we would see bright sources at the tips where presumably new stars are forming. And one of the first questions on a master's exam at UC Berkeley, if you're shown a picture like this and you're doing theoretical astronomy like myself, is they would ask, where in the Eagle Nebula relative to these pillars are the massive stars? And the answer would be up above. And what's happening is those massive stars are actually destroying the cloud that all these other stars are trying to form in. That all this very tenuous gas you see right here is gas that has been heated up beyond 10 Kelvin to thousands of Kelvin, maybe even more than that. And you can see, if you look really closely, you can see kind of like little wispy things coming off of the pillars. Those massive stars up here are starting to evaporate these pillars. And they are pillars only because the dense clumps here are shadowing, this material here is kind of stuck in the shadow of this clump, which allows it to remain, versus this stuff which got heated up and blown away. So those massive stars are a bit greedy in that once they formed, they're making it hard for other stars to form. And it turns out even before this happens, it makes it hard for themselves to form too. Because as they emit all this radiation, for example, a star that is 10 times as massive as the sun is 10,000 times brighter than the sun. How bright a star is a very strong function of mass. You increase the mass a little bit and its brightness goes up by, well, a hell of a lot. And so those big stars, they start emitting all sorts of radiation. They heat up and might actually destroy and make it harder for neighboring stars to form, and they make it kind of hard for for themselves to get bigger and bigger and bigger. Because as material is falling onto those big stars, the radiation they're emitting is pushing back so strongly that it's yet another thing combating gravity. Gravity is starting to pull things together. Thermal pressure is still trying to do what it can, but now radiation has joined the game, and radiation is also pushing back, preventing those stars from getting even bigger and bigger. Which is why we think that we don't see stars above like 30 or 40 times the mass of the sun is probably as big as you can get. We find a few exceptions, but they're exceptionally rare in the modern universe. So you only really get up to about 30 to 40 times the mass of the sun in our modern universe, and even then there are very few. As I said, the sun is an average star. Typically the stars you find are on order the size of the sun. One last thing that we see when we look in today's universe. Each of these objects we're looking at is a galaxy. So this green stuff we're looking at the radiation that's being emitted between galaxies. And this is an image in X-ray. So this green light that you're seeing here is giving us a sense of how much X-ray radiation exists in between galaxies. In X-ray radiation, again, different kinds of processes emit different kinds of light. X-rays are very, very energetic, which suggests that the material in between galaxies, so not inside the Milky Way, but maybe in between the Milky Way and a distant cluster of galaxies, is millions of degrees. Space is not actually that cold. The gas in between galaxies is millions of degrees. It's a little bit non-intuitive because if you went out into space, you would still freeze. And the reason is this, that there's just not a lot of stuff in between the galaxies. It's very, very tenuous. It's as close to a vacuum as you can get. If you imagine a box that's 3 feet by 3 feet by 3 feet, in this room, there's something like 1 followed by 25 zeros. If you imagine that number. There's that many molecules in that box in this room. In between galaxies, there's 12. Incredibly, incredibly tenuous out in between those galaxies. So even though each of those 12 particles are whizzing around at incredible speeds because they're incredibly fast and very hot, the chance that one is going to bombard you is very rare because there are just so few of them. So there is not enough to smack you and heat you up. So you would still you would cool faster than you can heat up. So you would still freeze to death in million-degree gas, as non-intuitive as that is. Anyway, the point is that this gas is very hard to explain. It's not only hot, but it's ionized. What I mean by ionized is that the hydrogen we see in between galaxies has lost its electrons. Neutral hydrogen is 1 proton with 1 electron whizzing around it. If you get the gas hot enough or energetic enough, that electron usually sometimes has a hard time staying attached to the proton. Even though they're electrically attracting one another, If the electron has enough energy, it will just fly off. Once the electron departs from the hydrogen atom, we call it ionized. All of this gas that we see in between the galaxies is both very hot and ionized. And why that matters is that we can't explain it using today's universe. You might think, well, the stars are emitting a lot of radiation, maybe they escape into outer space, maybe that heats them up. There's not enough. In today's universe, you cannot explain why, when I look in between galaxies in space, every part of the universe appears to be millions of degrees. The universe actually is a very, very hot place. So we have a conundrum, which is where star formation in the early universe might come in. So now that we have a sense of kind of how stars form in today's universe, let's see how well that can be applied to star formation in the early universe. Now I'm going back to 500 million years after the Big Bang. When I look around the Milky Way and Andromeda, I'm talking about 14 billion years after the Big Bang. So to go all the way back to when the universe was in a very, very young state, we need to remind ourselves of how the universe got there in the first place. So we need to think a little bit more about the Big Bang theory and remind ourselves what happened in the beginning. In the beginning, there likely was a bang. The universe began with a bang. The exact nature of the bang, that's another talk. What happened before the bang, who the hell knows? I can't answer that. I leave that to the philosophers. Or people who are currently thinking of ideas like the multiverse, where our universe may be one of many universes, which is a little misleading because, universe, one, all that there is. The joke, Alex Filipenko always tells this joke how, back before we started thinking about multiverses, the joke was define universe and give 3 examples. Now that actually might be possible. If we think of the multiverse theory, we might actually be able to give multiple examples of what a universe might look like. But that's not this talk. What we know from the Big Bang and what has been tested and borne out through observations by looking farther and farther back in time and using models is that after the Big Bang and from the Big Bang, the universe started more or less incredibly uniform. We know this by using things like the Planck satellite, which is a successor to COBE and WMAP, 2 satellites that most of the work was done out here in Berkeley. Nobel Prizes were thrown at it. Planck satellite is the successor, where it can look at the radiation that was left over from the Big Bang. So if you have a giant explosion that created all of space, there's some leftover radiation from such a boom. That radiation we call the cosmic microwave background, and we have been able to actually observe it and study it. And what these satellites find is that this is a picture looking over the entire sky, that it's incredibly, incredibly uniform. You might think this does not look uniform to me, but the difference between blue and red is to 1 part in 0.00001 Kelvin. So this is 2.73 Kelvin. This might be 2.73000001 Kelvin. This might be 2.299999 Kelvin. So by looking at the structure and particularly in this case the temperature of the universe, it suggests, given that this is so uniform, suggests that the universe started in a very uniform state. Right now, as I alluded, the temperature that we see is on the order of 3 Kelvin, which does not seem very hot. But that's because this is the radiation today. After the Big Bang, the universe has been expanding, and as gas and radiation expands, it also cools. So you can play the movie backwards. If it's a uniform gas at 3 Kelvin now, go backwards 14 billion years, and it becomes something that's millions of degrees Kelvin, or billions of degrees Kelvin shortly after the Big Bang. So the universe appears to begin in a very hot, uniform state. It also was not super interesting in terms of what elements were available. This is the periodic table. Again, most of these elements, except for the ones that are man-made, were cooked up inside of stars. But if I'm going back to before stars ever formed, we had this, where Big Bang nucleosynthesis, the the small amount of time where the entire universe was hot enough so that it more or less was one giant star. That only lasted until the universe was only about 3 minutes old. So you got 3 minutes to do all the chemistry you want to do. It turned most of the hydrogen it turned some of it into helium and a pinch of lithium. But by the end of the first 3 minutes, the periodic table and the composition of the universe more or less became fixed. At 75% hydrogen, 25% helium, a pinch of lithium. So not super interesting in terms of the elements that are available. The thing to remember here is that things like carbon and silicate are also not formed. They were down here, and we don't have those accessible at this early stage in the universe before stars formed. So then, given those very uniform, very hot conditions, how do we go from a universe that is more or less uniform and dark without stars to one that looks like this in today's age? The Milky Way is positioned here, and each of these dots is a galaxy. Just looking at a small piece of the sky and looking at how the galaxies are structured as you go farther and farther away from the Milky Way. So the universe today does not look super uniform. It's kind of patchy and clumpy. And there are stars in today's universe. So there are various questions we need to answer. The weird thing about it is, we actually, in today's universe, it's very easy for us to understand what the universe looks like. We can look with telescopes around how the universe looks today and how it looks a few billion years, down to about a billion years after the Big Bang. We have a good sense of what the universe looks like then because there were lots of stars around. So there was lots of things emitting light. There were things that we can see with our telescopes. We also know what happened. Well, we don't know what happened exactly at the Big Bang, but we know going from the Big Bang to about 400,000 years after the Big Bang, we also understand that region of time fairly well. Because that's when the entire universe was more or less completely uniform. And completely uniform is very easy to a mathematician or a theoretical astronomer versus something that is clumpy and random and there's all sorts of random little things going on. So we have a good sense of what went on up to 400,000 years. Then we have a giant question mark where there are no stars, or there are very few stars to see. So somehow we have to get from here to this clumpy universe filled with stars today. So while telescopes might fail, simulations can come in. So then this is where someone like myself can step in, who doesn't actually use a telescope. I've actually never used a telescope for my research. But I use supercomputers. So I use large simulations that run for months at a time, that use thousands of computers all tied together and working simultaneously as one computer, crunching numbers 24 hours a day. It's nice. A computer never needs to sleep. It just keeps going. And we can simulate how the universe might have got from this stage to this stage. Let's first address the clumpiness. So today's universe is kind of clumpy. The universe right after the Big Bang was very uniform. There, gravity provides an answer. Again, remember, the answer is usually always gravity. So this simulation, not yet my own, takes the universe as it might have looked, not too long after the Big Bang. So it's more or less uniform. This is not right after the Big Bang, so you notice there's already a little clumpiness, but it's, for better or worse, uniform. And now we're just going to roll it forward in time and let gravity do its thing and see what sorts of things we see. And since we'll see this time and time again, I apologize. Astronomers use a quirky unit to tell time, this redshift or Z. So it's backwards from what you're used to. So big numbers mean farther back in time. A redshift of 0 means today. So that number will continue to get smaller, but what that means is we're marching forward in time towards today. So as I move the time forward, gravity does its thing. And what initially started as very, very small perturbations, it wasn't completely uniform, but there were little bits that were a little bit more dense and a little bit more tenuous. Those over billions of years start to grow and grow and grow because even if you're almost completely uniform, but I have one more proton right here, and all the rest is uniform. that one proton still means there's a little bit more gravity pulling towards this region versus any other region. The more mass you have, the more gravity there is. And so that little bit of that little spot that's slightly overdense starts pulling in more and more material, and after you wait long enough, you eventually get this very clumpy, spider-webby structure, which matches very well actually what we see today. There's another movie that shows a more 3D picture of this. So a box of gas that more or less that started uniform with slight bumps, let gravity do its thing. And you notice that gravity kind of naturally creates this filamentary, spider-webby structure. So that's nice. It helps explain why the universe today looks like this.
If you let time go forward,
Yes.
go further,
Yep.
would it come to a point?
Would everything eventually collide? It depends. So there you have to, so the question is, if you let time go forward from today, what might you expect to see? And you're right, things would continue to clump more and more and more. Would everything eventually come together into one giant ball? That depends on things like the expansion of the universe and how fast it is, and things like dark energy, which I'm not talking about in this talk.
Well, just let it be like 1950 physics. Would it come to a point?
So in 1950, we thought the entire universe would recollapse on itself, yes. In 2015, we think it will expand forever at a faster and faster rate, so that would not happen. Yes, you'll have to get Alex Filipenko in here to talk about dark energy, and then he can really answer your question. So now, if we understand the clumpiness, again, gravity, now let's try to ask ourselves how you might form some of these very first stars. So remember back when we talked about what makes star formation easy, there were two things that helped star formation: get a lot of gas and get it cold. So it's likely that if we want to look for star formation in the early universe, when the universe is just starting to look like this, and no stars have formed yet, we might look at one of these dense clumps where that is the intersection of these spiderwebby filaments, because that's where there's the most gas in a small enough space. And just to remind you of the picture. So that is likely where these first stars were forming, which happens to also be, to give you a sense of scale, this is billions of light years across. So it's also very likely in these little dots, these regions here that I've outlined in boxes, these are also where some of the very first galaxies are going to start forming. So the first galaxies and the first stars are more or less forming simultaneously in this very early universe, because gravity is just starting to bring things together for the first time. But then if we look, what else helps stars, we run into an issue. The gas is hot. After the Big Bang left everything really hot, and as it's been expanding, it's been cooling off. But the universe at this point, 500 million years after the Big Bang, is still hundreds to thousands of degrees. That is much hotter than 10. And you're going to ask, well, we need something to cool off the gas. Dust. But is there any dust? There's not, because dust was the carbons and the silicates. And we don't have the carbons and the silicates yet, because we only have hydrogen, helium, and lithium. So are we screwed? Well, obviously not, because stars exist today, so presumably a first star had to form at some point. So we have to start thinking a little harder. So I would like to highlight some of the work of a colleague and friend at UC Berkeley, Athena Stacy, who did some of the first simulations on this, where she was one of the first simulations that found a workaround, found a way where even without dust, there's still a way to cool off the gas. It's through this rare reaction that happens if you take 3 hydrogen atoms and throw them together, which you might imagine takes a very precarious and very special setup. If I have things roaming around the room randomly, the fact that 3 would perfectly collide with each other at one point happens much rarer than, say, any 2 random ones running into one another. So you get these rare 3-body reactions, which occasionally do happen. And when they happen, if they happen with a big enough smack, 2 of the hydrogen atoms can lock together, which to lock them together takes energy. So in making this molecular hydrogen atom out of this 3-body collision, some energy is lost. The gas cools down a little bit. And then it turns out once you have enough molecular hydrogen, it has its own ways of cooling off. And then they take it the rest of the way. The electrons for the molecular hydrogen have an easier time releasing radiation. But to get the process started, you need this rare and initially overlooked three-body reaction. So she ran simulations where she started with something like what you might see after a Big Bang event, let it collapse to something like this. But then she didn't stop here. She zoomed in on these regions and kept the simulation running, taking into account the additional chemistry and additional physics. And she found that in these spiderwebby clumps, and this is zooming in more and more and more, you eventually can get the gas cold enough that it can start to clump into what it starts to appear as like a disky shape, where you have hundreds, maybe thousands of solar masses, so something that's 1,000 times the mass of the sun, all that gas crammed into a quarter of a light year. To give you a reference, the Orion Nebula that we looked at before, that was only on order 10 to 12 light years across. And that had about 1,000 times the mass of the sun. Now you have that same amount of stuff in a quarter of a light year. So you've crammed a lot of stuff into a small space. And you've managed to cool it down to something like 100 Kelvin, so 100 degrees above absolute zero, which is not 10, but it's not 1,000. And remember that there are two parts of the prescription. That if you have to keep it hot, a way of overcoming the fact that it's hot is just throw more mass at the problem. Because then you get more gravity, and maybe even though the gas is hotter, maybe there's more gravity that can still beat out that thermal pressure pushing back. So then, the question, which now then becomes my thesis, is what happens from this point onward? You have 1,000 masses, 1,000 times the mass of the sun in this very small clump. It's now at a point where gravity can do its thing, and gravity will win the battle. But is it all that 1,000 times the mass of the sun, is it all going to collapse into a single star? So you get a single star that's 1,000 times the mass of the sun? Remember I said the sun is an average star today, and you typically don't see anything above 30 to 40. Now I'm claiming 1,000. Turns out that actually can't work. That actually is a problem, because the bigger the star gets, actually the more unstable it gets. It's very hard to keep a star stable above 100 solar masses. It tends to kind of blow itself apart. It's emitting so much radiation that it kind of evaporates itself. But you can kind of get around that with these first stars, because there's only hydrogen and helium, which interact with radiation differently than dust or differently than heavier elements. So models allowed for these stars maybe to be up to 300 times the mass of the sun, but 1,000 is still ridiculous. So we have to come up with a theoretical model, or then we have to test this out in simulations and see what we find. So here's our model. We don't think that you will get a star that's 1,000 times the mass of the sun. We think you will get a star that's something like 150 times the mass of the sun. That's a good ballpark. Where the average star, again, compared to today, where the sun is an average star, where the average star when the universe was only 500 million years old was 150 times the mass of the sun. It's over 1 million times brighter. Each individual star was over 1 million times brighter than the sun. How do we think that happens? The first two steps will look familiar. Again, gravity. And then as you get this stuff that's kind of mixing around, you'll get some sort of accretion disk where the gas is falling into a disk. But in this case, there's so much stuff that you actually also have stuff falling not only from the disk, but also above and below the star as well. Because in this case, you really do, in a sense, have unlimited supply of material to make the star as big as you want. And thermal pressure is no longer doing anything at this point. But remember back when we talked about how high mass stars in our universe, the radiation starts to play an effect. Once the star gets big enough, the radiation coming off the star starts to fight back. We think that's what happens with these very first stars. That once the star gets to about 20 times the mass of the sun, So it's about 80,000 times as bright as the sun. The amount of radiation it gives off starts to fight back, and so all this very tenuous material above and below the disk, where the disk is much thicker, that's where most of the mass is, but then you still have all this stuff kind of above and below. The radiation pressure kind of blows a bubble that prevents the mass from falling in from the top and from the bottom. And so the only way for this star to get bigger and bigger and bigger is if it can accrete through the disk. So that cuts off a little bit of the mass. So again, if the star wants to get bigger, if it wants to get to this 1,000 solar masses, it has to go through the disk. That's the only network, that's the only channel open to it. So let the star get bigger and bigger. Once the star gets to be around 100, 150 times the mass of the sun, it's now over 1 million times brighter than the sun is today. It's emitting so much radiation that even that dense disk gets obliterated. We call it photoevaporation. That the radiation from that new star is so copious that it just evaporates its surroundings. And so any material that's trying to fall in via gravity, radiation impacts it, smacks it, and sends it on its way. So if none of the mass can make it onto the star cannot continue to grow. And so then we use that as a way of estimating the final mass of the star.
So the radiation is not moving the material, but it's making it evaporate, increasing temperature.
I would say it's doing both. So it's increasing the temperature, and as a result, then that material is moving around much faster, and it's being sent flying, because you can think of the radiation pressure as like me throwing a baseball, at an object. If it impacts, it will impart some oomph in the opposite direction. And that gas then becomes so hot, it's moving around at such fast speeds, it has a very easy time flying away. Gravity cannot pull it back in time. So do we actually see this in simulations? I've conveniently set up this talk so the answer is yes, but we can look a little bit at what the simulations look like. So this is an example I've zoomed into one of these regions that Athena has simulated, where she was looking kind of on the global scale, light years in size. I'm now looking, this is on order maybe thousands of astronomical units, so something that's like 10 times the size of the solar system, something like that. And right down there in the middle, you see is where the star is forming. You can see there's kind of a little disk that's forming. This region is maybe hundreds of AU, so about the size of the solar system. And now we're going to let the simulation go. That star that you can't see because it's kind of buried in the little disk that the simulation is showing. That star will continue to grow from right now, where it's about 5 times the mass of the sun, up until it's about 80 to 90 times the mass of the sun. So first thing that happens, all that radiation blows a big bubble perpendicular to the disk. So now the only way that material can make it onto the center of the star is through going through these thin regions here. Nothing is happening out here. You see all the arrows are pointing the opposite direction. That stuff is so hot, and is being impacted by all that radiation pressure, that it's going the opposite way. As the star grows and grows and grows and grows, it emits more and more radiation, so eventually that disk around it just becomes obliterated. And notice that then all the regions around the star, which remains in the middle, so now there's nothing. Now there's nothing heading towards the center. All that radiation has just obliterated its surroundings, which prevents any additional material from falling on to the center of the star. Let's watch that again.
What is the light pink region?
Yeah, so it's increasing temperature from blue to red. And the white region, there's kind of like a torus that forms near the very end. It's actually just more of an aliasing artifact. It would be yellow, but the way it's trying to project the image, it makes it look a little white. So again, material on the top and the bottom is now prevented from making it onto the star, so the star can only grow through these channels here. And as the star gets bigger and bigger and bigger, the radiation it emits gets more and more copious, till eventually, even in that very dense disk, the radiation eventually blows itself apart. And no matter where that material is falling in from, it has a hard time making it to the center of the star. Yeah, so you're talking about this torus?
Yes.
Yeah, it would be the same as, it should be yellow, but it's an aliasing issue. Just of trying to render this in 3D. You have a very hot, the key is that you have a very hot region surrounding the star, which is preventing any additional material from really making it onto the star. So this is interesting, because this suggests that the early universe was very different from the universe today. You have a typical star that was something like on order 100 times the mass of the sun. So what can we take this forward, and what does this imply? These are just visualizations that were made a few years ago, trying to get a sense of what these pop 3 stars that we call them, population 3 stars, which is more just fancy talk for first stars to ever form, compared to pop 1 stars, which are today's stars, and pop 2 stars, which are stars that formed a few billion years ago. So these first stars, once they form and once they grow in size, they start to blow giant bright bubbles around them. The universe is starting to be filled with light. But this light has to work its way through all of the material that is surrounding it. So if we go to the next simulation, or rather the next visualization, if we play this movie forward for maybe 500 million to 1 billion years, this gets very interesting, because in the spider web, where all the dense material is, the light has a very hard time making it through because there's a lot of stuff in the way. But in between those filamentary structures, the light has a very easy time just soaring through the universe. Remember, inside these filamentary web structures is where the first galaxies are going to form. So in between the spiderwebby filamentary structures are going to eventually become the voids in between galaxies, which are now being filled with this copious amount of very bright light, which helps both to heat up the gas and ionize the gas, the tenuous gas that is in those spider webs, or in between that spiderwebby structure. This is a cool one. Visualizing the entire universe as a box, more or less. And it's imagining, if I have stars and new galaxies forming all over the place, it kind of becomes a universe Swiss cheese model, where the light from these first stars and first galaxies starts heating up all of its surroundings. And the galaxies themselves take longer to cool off, but in between all the galaxies and in between all the spiderweb structure becomes filled with light and filled with energy, which helps keep the gas hot and helps get the gas ionized. And so this we call the epoch of reionization, a moment or a region in time when the universe was about 500 million years old to maybe 1 to 2 billion years old, where the universe went through some sort of transition where it went from more or less entirely neutral to very hot and ionized, like what we see today. When we look in between galaxies today and see everything is ionized and everything is very hot. There was some point where that transition was made, and we think it happened in the first 1 to 2 billion years. We think that these stars might have played a substantial role. And my dissertation actually will try to assess exactly how much of a role they played. Because if, on average, most of the stars were like what we saw in that simulation, where they were very big, emitting tons of light, they actually could be a significant reservoir, where they could be the ones that are providing the energy to ionize all that gas in between galaxies and in between the filaments. If it turns out that that one particular simulation was a fluke, and we do more simulations in different kinds of environments and find, on average, these first stars were something like the sun, or something like 10 times the mass of the sun, then they're not emitting nearly as much light. That might actually suggest that there's something else at play here. So the idea is to assess what happened, and how much of a role did these first stars play when the universe went from one of darkness to one filled with light, where the universe, on average, if you look in between the galaxies, is very, very hot, and particularly very, very ionized. And then these first stars, so there's also another type of star called POP3b stars, which means they're not the very, very first generation of stars, like what I'm trying to simulate, but they are the second generation of stars. So the stars that might have formed as a result of the chaos that was created during the formation of these very first stars. Because they're emitting lots of light, they're making gas hot, they're throwing gas all around because they're emitting a lot of radiation pressure. It's possible that that can then trigger additional star formation perhaps somewhere else. Eventually these first stars die. They will likely explode as supernovas since they are so big. That can then trigger, that supernova is one way we think that you can get things like the Orion Nebula, because the supernova explosion acts like a giant snowplow in a sense, and that explosion piles up gas that might eventually then form something like the Orion Nebula. And the Orion Nebula eventually gravity does its thing and forms new stars. But those are where the heavy elements start to get made. The first carbon atoms, the first oxygen atoms are being formed in these POP3 stars, these very first stars. So these stars are not only bringing light to the universe, they are bringing the heavy elements, which eventually will, through many generations of recycling through stars, eventually form something like the Earth and the Sun and us. So I like to think that the first stars, as I alluded to at the beginning, is when the universe started to know itself. It started to become aware that it exists and it can interact with itself, because these stars, as they heat up the universe and toss gas around, and that triggers new stars to form, and then galaxies are forming because of where these stars are kind of residing and taking place. The universe becomes a much more interesting place, and it starts heading towards one that is appropriate and capable of developing intelligent life. Which I would like to believe, the fact that intelligent life can develop, it's not just a whoops of nature, but that that it might actually be written into the fabric of the cosmos, that a universe tends to something that can evolve into intelligent life, so that we can reflect when we're not staring at the Golden Gate Bridge and realize the profound impact we have had on the universe and how much the universe itself has had a profound impact on us. And with that, I would like to end. Thank you. I'm happy to hang around and answer questions. I'm not sure if the person's going to dismiss people or if I can answer questions for a little bit.
Just a few questions, and if you will, repeat the question.
Okay.
Two questions. How would a star that's made only of hydrogen and helium and a lithium behave differently than a star that has traces of other elements? Second question, what can we realistically hope to empirically observe that might validate or not?
Good. So the first question was, for a star that only has hydrogen, helium, and a little bit of lithium, how would they perhaps be? Would they be intrinsically much different than, say, or how different would they be compared to like the sun, which has all sorts of different kinds of elements? So it turns out they're actually not that much different. If you look at the composition of the sun, it is more or less 75% hydrogen, 25% helium, a smidgen of everything else. Where for these very first stars, everything else is just lithium. What makes the sun what those other elements make interesting for the sun is that they imprint their fingerprints on the starlight that's coming off the sun. And when we look at local stars, we get an imprint of the type of elements that they have. And that actually allows us to determine things like the age of the star and the size of the star based on the relative amounts that we see and how strong those particular dark marks, those dark fingerprints are on the starlight. But in terms of how the star operates, no different. What's going on in the center is still hydrogen to helium. The exact process might be a little different from the sun. So the sun does it by a process called the proton-proton chain. It's likely that Population 3 stars would do that for a little bit until it forms a little bit of carbon, nitrogen, oxygen, and then there's another cycle that pops in called the CNO cycle, the carbon, nitrogen, oxygen cycle, which operates easier for higher mass stars like these guys. But until there is any CNO, it will operate just like the sun. And then the second question was, can we ever hope to observe anything related to this? How can we validate, my awesome simulations? Your words. So you're right that we will never be able to individually observe one of these stars. These stars being so big, something I didn't mention is the amount of time a star lives depends on how big it is. The bigger the star, the shorter its life. The sun will live for about 10 billion years. Something that's 20 to 30 times the mass of the sun might only live for something like 1 million years. So you imagine these guys that are hundreds of times the mass of the sun, they are not living for very long. So any of these stars have long been dead. So we can't hope to individually see these individual stars, but we can hope to see some of the very first galaxies that were formed and have perhaps some of these stars or some of the second or third generation starlight in them. So while it will be too hard to observe an individual star, if we look at a galaxy like that red smidgen, that red blob I showed, that might be an example where even though it was just a red blob on the screen, I can look at how much light is coming at different wavelengths or different kinds of light is coming from it, and I can fit that to a model of, well, if that galaxy was filled with predominantly small stars, the type of radiation we would expect would be different if the galaxy was filled with a predominantly of big stars. And also this epoch of reionization, again, whether these first stars, if they did play a role, whether these first stars are big or small, affects how long this process takes. It might not actually be 1 billion years. This might have happened, at a little bit down here, maybe it's up here. There's some wiggle room into exactly how long this process took. And there are new telescopes, particularly ALMA, which is a new telescope in Chile, that will be able to probe this region here a little bit more. Again, not looking at individual stars, but looking at being able to look at all that tenuous hydrogen in between the galaxies and see when it started making a transition from being predominantly cool and neutral to something that was hot and ionized. And so then we can match what we see by those observations to our models and see, that will actually be how we assess whether these stars played a predominant role or not. That will be a good test. All right.
I don't know exactly how to answer this question, but why is it that in the atom, it's been the same story? Outside of the atom, there's all this change. So another way I was thinking of asking the question is, are atoms to the universe as black holes or to dark matter?
So I'm going to have to try to think of of your question. So atoms themselves, like what actually makes up a hydrogen atom, is no different today than what it was in the early universe. But through nuclear reactions, so that you can think of that in our universe, there's a fixed number of protons, there's a fixed number, of electrons. That's not completely true, but you can think of it that way. And then through nuclear reactions, whether all of that is hydrogen or helium or lithium or something else, nuclear reactions can change the types of elements that are out there. But it's all still the same protons, neutrons, electrons, that sort of thing. So it's not that matter is kind of lost when it's locked up as an atom. It can still change, but it's still going to be something that's what we call baryonic matter, or matter that's made up of protons, neutrons, electrons. Not sure if that got to your question or not. But maybe we can talk after, and you can try to elaborate a little bit. All right.
I think there's a gap between these early stars and the galaxy, the formation of the galaxy. Is that a whole other area of your research, or is that something that you're going to see kind of out of your work?
I will not see that. I'm zooming in a little too much. I'm looking at really what's happening for these individual stars. But But you're right that what's going on kind of a little bit more globally, not globally as the entire universe, but kind of zoomed in. You're right. So the question was, I realized I forgot to repeat it, is that there seems to be a gap between the first star formation and the first galaxy formation. Will I be able to assess or help validate or kind of resolve that or any questions that arise there? And there might not be that much of a gap, because again, while this is all happening, the first galaxies are also forming. So they are more or less going on, and this is very hand-wavy, more or less going on at the same time. But you're right, more simulations would be able to show exactly how these first structures, these very first galaxies are starting to form. And then inside them, you might have things like these first stars.
I'd like to present with our thanks for being here tonight and giving us such a wonderful talk.
Well, thank you. And I can gladly hang around and answer more questions.
I
I have a rod. Yes.